OS22, the VGA rabbit hole. Let's jump right in. Here's some links, more in the description. But here's what we're going to talk about today. We have all these different topics. It's all summed up in a blog post. You can find it at docs.pkos.pagekey.io, and you'll see it's quite long and it goes into great detail. But let's go for a quick overview of what's in that article with this visualization. So what's our motivation here? Well, in OS15, you will see that we had some nice pictures that we were able to draw on the screen. Each pixel on the screen was accessible, no problem. The only issue was you couldn't get back out of VGA mode once you were in it by hitting escape. So you couldn't do any more text mode. Once you get in there, you were stuck. Before we started this video, the main branch of PKOS had this, where you had a little bit of the screen cleared out and it looked really weird and you couldn't draw anything, but you can get back to text mode. Now we have this abomination, and you can get back to text mode too, except for there's this little animation of a rectangle that I left up, which stops you from getting back. But otherwise, you can switch back and forth, and most of the screen you can draw on too. All of this white part and the purple part, that's all drawable. We just have this little bit in the middle that contains font information that we haven't figured out how to get rid of yet. So that is ongoing work. Here's a bonus. This is when the screen got really messed up at one point, and it looked pretty entertaining. Just figured I'd throw that in there. So let's talk about what we learned and some other good lessons. Overview of VGA registers. So how do we get and set values for the VGA registers? Well, it turns out that there are so many registers for VGA, dozens of them, that we need to save space on I/O ports somehow. We can't have an I/O port for every single register like you can with some other hardware. So what the solution that they came up with was address ports and data ports. The address port takes an index of which register you would like to operate upon, and the data port either delivers you data or you send it data to change the state of the VGA hardware. So as an example, the attribute controller has an address port of 3C0 and the data port is 3C1. And if we look at the attribute controller, there's a lot of stuff stored on there. There's quite a few registers, palettes, 16 of them, attribute mode register, overscan color register, all these different registers. In order to interact with those, we follow this process. So you read the address port first and store it in a variable. This is important because if someone else is about to use that as well, if you're in an interrupt routine and your function gets interrupted, whatever, you need to be cleaning up after yourself and be kind, rewind, put back the address port the way you found it. So first we save it, then you're going to write the index that you would like to operate upon. This is where you're going to select which register you want to do things to. That's going to be your index. So if you want to access the overscan register, you're going to write that to the address port. Then you're going to read or write to the data port. So if you want to set the value of the overscan register after having written the address port, you're going to write to the data port. Similarly, if you're interested in what the current value of that register is, once you've set the address port, you're going to do an in byte. You're going to read in from that port into a variable so that you can operate on it. And then the last step, do not forget, is to restore the value of the address port back once you're done. So these are of course in and out operations in assembly, but that's the basic flow. So that's getting and setting values. The next topic is the I/O select bit, which was a little funky. So if you're reading the documentation for the external registers, the miscellaneous output register, it says this little paragraph, and it says the bit in the external register, miscellaneous output register for I/O address selection sets the CRT controller address. If it's a 0, blah, blah, blah. Basically, whatever this bit is set to affects which address and data ports you have for the external and general feature control register or for the CRTC. You can see that they have 3CA, 3XA, where X changes based on the value of this. It's either a 0 or a 1, right? So there's only two possible values. Same thing here. It's either 3B4 if it's a 0 or 3D4 and 3D5 address and data respectively when it's set to a 1. So that's a little idiosyncrasy that you have to pay attention to as far as this bit affecting which ports you're using, which is a little strange. So the next topic, AC register. I just found that OSDevWiki refers to 3C0 as being a confusing port where you have to read from 3DA so that this port is in the index state. Otherwise, you're not sure which state it's in. Apparently, it can be used for indexing or data. I don't know, that was not mentioned on osdever.net, but the same port number can be found on the address register for the attribute controller. So to be safe, I did insert some code to do a read on 3DA before doing anything with the attribute address register. Next up, let's talk about lessons learned. So I definitely learned that VGA is not a state machine. You can't just verbatim read all of these registers and then restore them exactly as they were and expect things to work out perfectly, because some registers being written affect the other registers. I'm not sure exactly how, but maybe in a future video I'll figure it out. Either way, you can see a quick overview of each of the register groupings, and I think these corresponded at one point to separate hardware, separate chips. The attribute controller has a bunch of palettes and some other things here. The CRTC, cathode ray tube controller, has tons of registers controlling very intricate things about how the beams are flowing and all those things. I don't understand it, but there's plenty of options to change with these registers. The external general has the miscellaneous register with the IO address select bit we talked about, as well as some other things. The graphics controller register has the graphics mode down here, which is pretty important. It also has the MISC register that sets whether you're in text mode and some other things. Who knows what they all do. And the sequencer likes to mess things up if you set it the wrong way too. The reset register allows you to turn off the sequencer, which lets you change the other fields without, I guess, having them immediately reflected. The clocking mode, map mask, character map select, all these things do stuff, but the details are a little bit nebulous for me. You can select different fonts using the character map select and then the map mask, all this stuff. I don't know. It gets pretty complicated, but at least you can see that the registers are, they're there, but operating on them and setting them in the right order can be very complicated. Another lesson learned was that when I was printing things, I was not setting the text mode attribute byte. So if we have this PKOS prompt in our console, what's going on is that in video memory at B8000 we have a P character, but at 8001 we have an attribute byte that is telling us that the text should be white and the background should be black. So that's a 7. That basically selects, the color and other attributes of the text. The next byte is the next character and then its color and background, and then the same for the O and the S. So that's how the memory is laid out, with each byte for the character and then the byte for the color. So what was happening is all of these color attribute bytes were getting cleared when we got into VGA mode, and they were set to 0 because we were painting the screen black, and I would go back into text mode and see only a black screen because 0 means black font on black background. So I needed to update my lazy print method to set that second byte also when printing characters to the screen, and that helped things out quite a bit. I also learned a little bit about VGA fonts. So if you have an A character in VGA fonts, it's really just 128 bits, and zeros mean the background color, which is a dark blue in this picture, and ones mean the foreground color, which is white. So you can see that if you store in memory this series of bytes, you're really just painting the character with zeros and ones. So that's how that ends up getting painted. Another cool thing that happened was I was copying memory incorrectly. What was going on is we were taking B8000, the start of video memory, and backing it up to 10 B8000, which I thought was a fine enough memory location to store things, and then restoring it when we were done drawing. But thanks to John Strong, we chose a better memory address, 1B800, which this one just seems to be out of range or something. It wasn't working too well. Once we switched it over to 1B800, things started working as far as backing up memory and restoring it. So that was good. That arrives at the partial fix. So you can see the purple and the white are the places on the screen where we're able to draw. And that was found by trial and error of just drawing it on the screen, switching back to text mode and checking which font pieces were corrupted. And it turned out that these little striped areas were the only spots that corrupted the text. So the rest of this is free to draw however you want, but unfortunately we have this messy third of the screen that doesn't quite work yet, and the solution is TBD. But I know John Strong has been working hard on it, and maybe I'll be able to find something too. We'll see. Next steps, so we can continue with the brute force fix that you see up here for VGA. VESA could be an option. Apparently it's a more modern display standard with maybe better documentation, although the trade-off is it's not quite as widely supported as VGA, but probably still pretty well supported, right? But I was taking a break from this project and probably will continue to work on Boom Languages, which is another PageKey project you can check out at boomlanguages.com or docs.boom.pagekey.io. It's recently open sourced. And then of course we're going to work on the file system eventually, and that's going to be IDE or PIX or whatever we need to do to write to a hard disk and read data from it. So that's the plan, and that's OS22, the big picture. Feel free to read the article, and I'm trying to stream pretty often too, so that you can come along for the journey as I figure these things out. But yeah, that's about it. Thanks for watching, and hope to see you for the next one. I always forget to say, don't forget to activate the interrupt routine on that subscribe button. And of course, if you want to join the Discord and chat, you can click that button at pagekey.io. See you next time.